Hello everybody, I'm Zara17 and I'm back here with a brand new video, and this is about something that I guess I found sort of while I was playing with graphs and everything. It's related to the flow function, ceiling function, and a function to round numbers, and I think it was really interesting to find. But before I go over the exact formula that I found, at first I'd like to, you know, just define what the flow function and ceiling function is, because I feel a lot of people don't actually know about it. So I'll be starting with that. So the flow function basically, let's assume x is going to be any real number. So let's assume x to be around, like, let's say 3.4, right? So 3.4 over here. So now, as we know, 3.4 lies between two integers. This is a real number, and between any two integers there's like uncountably infinite number of real numbers, but we won't be going over that. So it lies between the integers 4 at the top and 3 at the bottom. Okay. Yeah, and 3 at the bottom, right? So as you know that a room has a floor and a ceiling. That's again basic information. And so a room in a room, the floor is always at the bottom and the ceiling at the top, right? So here's the ceiling and here's the floor. So as you can see over here, we've got a similar representation over here where 3 is sort of at the bottom. So when you put in x for floor of x, you get the bottom value. The between the two integers that it is in, the lower integer, so basically 3 over here, right? And then ceiling, as it is on the top, you get the value 4. So you get 4. And yeah, it is a fine assumption to make that floor of x plus 1 is just, ceiling of x. That's a perfectly fair argument to make. But you have to have something that goes well with a floor, so a ceiling, so it makes sense, right? So we have this. So basically, regardless of what number the real number is, it'll always give, like, floor of x will give the bottom value and ceiling of x at the top one. Unlike the rounding function, which will give a slightly different result based on this part, basically the decimal part over here. So depending on that side. So like we have 3.5 over here, but I'll be going over that shortly. And so now that I feel we have gotten a bit of a feel for floor effects and ceiling effects, I'll be going over a couple problems, basically going over it so we can understand it further, right? Okay. Okay. So now that you have a screen cleared, let's go over a couple problems. Let's assume x equals, let's say 21.9. Yeah. And now we have to find the floor of x. Okay, we have to find the floor of x, and let's say the ceiling of x plus 2. Yeah, we got that. Okay, so let's go over here. So floor of 2.9. That's when we substitute the x for 2.9, we have floor 2.9, correct? And see, the flow of 2.9 is still going to be 2, even though it's so close to the value of 3. It's still going to be 2, because again the bottom. So again, as it's the bottom, 2 and 3, here we have 2.9, so it's going to be the bottom flow. Okay, and the ceiling, since we have x plus 2, it's going to become 4.9, and the ceiling is going to be, for this value particular, x plus 2, ceiling of 4.9 is going to be 5, right? That's just going to be 5 over here. Okay, so we have that cleared up, right? Now let's define our sort of rounding function over here. So I'll be going over the integer part right now, like, so just an integer rounding, but as we go, the formula will work for like other values, like rounding something to its nearest tens or hundreds or whatever number and its multiples you like. Okay, so like first of all, some of the uses for the flow function and ceiling function, well, mostly the flow function, is to basically get the integer part of any decimal number. So if you have something like root 2, like over here, you have something like root 2, whose digits are basically going to be 1.41 something, right? It's going to be, yeah, 1.41. I apologize for the delay. Yep, 1.41 something, right? Let's add the parentheses. So, when you just want this part, right? We know square root of 2, so we can just take one. But like, in somewhere like programming where you need to take in the user input and everything, this is going to be handy. So like, let's say we want to take the first digits, let's say the first two digits of, well, the first digits of, well, any number. So basically it's going to be like let's say of any input base x, where x can be any number, right? And most likely this is going to be irrational. It's going to be irrational, correct? Yup, most of the times it's going to be irrational. Okay, so you just want, so let's say we just want the first two digits like this. Okay, only this, right? So what we do, first of all, in the encoding, x is like, the input is taken. So let's say over here, x is just, let's say it's 3, right? Which is gonna be, somewhere around 1.7, right? Give me a minute. Yep, somewhere around 1.73, goes on forever, but that doesn't matter because we just want these digits, right? So what we do, we can take the square root over here, right? So we have the square root of 3, and what we do, so we have 1.7, so we have this gargantuan enormous number. And so now what we do over here is basically we multiply this by 10. So we do 10 to the power of root 3, which will give us 17.3 3 dot. It'll go on for infinity as it's an irrational number. And then what we can do over here is use our flow function. And by the way, for easier notation over here, flow function is also written in short using a couple of fancy L's, and ceiling function is just opposite L's. So this is just floor of x. Okay, this is floor of x, right? This is floor of x. Yeah, and this is gonna be ceil of x. Let's get that clear. Okay, no confusion. So when it's just an L, it's the floor of x, and when it's an upside down L, it's gonna be ceiling of x. Just so we have that clear. Okay? Now, so we have this function over here. Now what we do, we find its floor. So we apply this, and we're gonna get 17, right? But we don't want this as 17. We want this as 1.7. So we simply divide this by 10, and voila, we have 1.7. So for something like this, a program like this, we could just take in root of x, where x is whatever the input is given by the user, times 10 to find the floor of that, and then we divide it by 10 again. So yeah, this is where it is. This is a lot of times that is normally used, and it is also used for finding the roots. The number of digits any particular number has using the logarithms formula, where only the integer part is needed. The flow function is absolutely useful. now that we have that, we know exactly what it's used for. Let's go on to define the function. Now, as we know, the function is sort of a, so now, if you want to do this, you could go about a few different ways, such as, for example, you take the number 3.4. So what you could try doing is basically converting it into fraction form, 34 by 10, right? 34 by 10, which is gonna become 3, which is gonna be 3 by 4 by 10 in, mixed fraction form, and then you can just cancel this out, and that's gonna be the flow. And as for ceiling, like I said, it's just floor x plus 1. So you can just write it as 4. You could go about doing that, but first of there's one problem. Problem number one is that, like, our current goal right now is to sort of mathematically define it with a few formulas, and canceling out this part over here, we don't really have a mathematical function for that, at least one that I know of. So that doesn't really work over here. So basically there's no formula to define it, right? So that's a bit of a problem. So no mathematical math uh, functions for this, right? So, like, not functions exactly, but more the calculations. Yeah, no math, no math calculations. So no math calculations. So like, yeah. So there's no math calculations for this. And secondly, this does not account for a problem of irrational numbers, which also come in the form in real numbers, right? So it doesn't work for irrational numbers basically, because you can't really write them in fraction form. But sure, you could estimate, but again, that doesn't really fit our purposes over here. So not for irrational numbers. And irrational numbers, as we know, also come under real numbers. And our goal right now is for any number x which comes under real numbers, right? Not for irrational. So here's a solution that I sort of found basically, and this is based on what a lot of people say about the flow function. Basically, what you do is just, yeah, let's take this in for a bit, and I'll be going over what a lot of people say that sort of led me to come to this formula. Done. Yeah. Yup. So what a lot of people say about the flow function is that the flow function is basically you take any number 3.4, right? Let's say for example here, and basically you take 0 over here. You add 1, right? So you get 1, but that's not quite 3. So you add another one.
Another one.
Yeah. We add another one to this, and that becomes 2. Still not quite 3. So you keep adding ones like this until you get 3, or like whatever is the integer part of this number, right? Now it is fine and dandy, and this is where we're really going with this, but it's not really mathematically defined right now, so you see, right, what's the problem over here? It's not defined mathematically, it's just a process sort of to get stuff to work. Okay, so I was playing around with graphs. I was really curious about this problem, so I started playing with graphs and I was thinking, how could I figure this out? And I did try the fractional method I just showed you a couple seconds ago, but that didn't really seem to work. And then there's repeated addition over here. And while most people, when they think of repeated addition, their head goes towards multiplication, right? The head just goes to multiplication, which is a fair thought, honestly, going to multiplication, because that's what it is at the end of the day. But it's not quite that. It is something else that is related with well, I don't know how to describe it. It's more so like, I guess, complicated multiple addition, like addition, like repeated addition, with series and whatnot involved. And I believe the astute among the viewers might recognize what I mean over here. Yep, I'm talking about summation. So let's clear up the board, and I'm going to show the formula now and explain how it works basically. So summation, okay. Um, so we have x over here. X is the number that we want to, find the estimate right now. Okay. So the rules is basically for, let's define a function round. Okay. Round x, where round of x is basically, where this is basically going to be, where, like, for example, x is 3.4, correct? So in a case where, like, this decimal part is just lesser than 0.5, so where this value is lesser than 0.5, this just it just gives the floor of this value. Okay, so it's gonna be the floor. So it's just one function using two other functions that we're trying to define here, but don't worry, we'll get them. So you just find the flow. And if it is greater than or equal to 0.5, it finds the ceiling. Okay? So the ceiling. I apologize for the bad handwriting again. So we have this set up, right? So we're gonna be defining the round function first. So yeah, we have rounding over here. Again, here we'll be talk about rounding to the nearest integer. I'll be going over rounding it over to the, like, nearest multiple of whatever integer you like soon enough, just in a bit. Okay, just give me a few moments. Yep, let me define this. So we have this formula over here. So x is the number that we want to round over here, and n is just 0. So, like, 0 time of what happened, and over here we put in 1. So just add 1 multiple times until x. Now the property that I want to go over here is that, thing is, this function, right, is just gonna add it. So this part you see over here during summations, it automatically just sort of estimates that, it just sort of estimates it to the nearest integer. So the round function. So basically, if this is 3.2, it will directly estimate it to 3, or if it's like 3.9, it's going to directly estimate it to 4. So the summation is basically doing the work for us. So it's basically just doing the flow function just in a more sneaky way. But summations are a mathematically defined, way of calculation. So we'll be using that. We have this. Now we do this minus summation of, yeah, so summation of minus x n by 0 of 1. So this part enables us to find the floor of even negative numbers, so basically round number. So you can try the formula out for yourself, but let's assume x equals 2.3. I'll be opening up my graphing. I'll be opening up my uh, graphing software for this. Just give me a minute. Okay, so the graphing software is ready. But before that, I'll just like to go over a more complicated version of the formula, the more generalized form, basically. So, the basic generalized formula is going to be x by the absolute value of h, the number whose multiple you want to estimate the value to, over here h, and n equals 0 for this, minus x of h, the summation again, h n equals 0. And I'll be going over the formula soon in my graphing calculator so that we can actually play around with the various values. So there we go. Okay, so as you can see over here, this is the function basically that we've set up, and this is a more complicated version, and I'll be explaining what each variable does. Now, so we set this as 0, k as 0, and the purpose of k I'll be going over shortly in a bit. It's related to the floating function and the ceiling function. So over here we have x to be the value that we want to estimate, and h is the multiple that we want to estimate it to. So over here it's 1, so that means whatever for any input of x, it just estimates it to the nearest integer. Now if I were to set this to somewhere like 10, for example, it would take in the input such as let's say x equals 3, not 3, sorry, x equals 3.2 over here. So if we put in 3.2 over here and we put in 3.2 over here, what we get basically is the answer, which is 0. So it's just going to estimate this to 0. Now for example, if we set this as 9.2 and 9.2, it's going to get close to 10. And if we set this as minus 9.2 and this is minus 9.2, it's going to estimate it to minus 10. So that's the formula that we are looking for when k equals 0. And this is not just limited to ones or 10 or multiples of 10. You can do this with any integer. So let's say we're going with 4. So it's going to round it to the nearest multiple of, 4 or 3 or whatever integer you like. So it's a more generalized formula over here for the rounding function, basically, right? So basically, the rounding function takes two inputs: x, the number that you want to estimate, and h, the number whose multiples you want to estimate it to. So that's the rounding function for you. And I'll be going over the floating function and ceiling function right now. Okay, so I've set this back to normal where we're estimating each number to the closest 10th value, right? So we've got this set up. So over here, the x-axis value is going to be the value we're entering, and the y value is going to be the number that it's estimating it to. So over here, k plays an important role. When we set k to 0.5, it changes the entire equation to a ceiling function. I'll show it to you. Ceiling of x. I'm gonna just change this to 1 so that it's easier to see. Yeah, it perfectly aligns as you can see over here. And if x is equal to 0, it's sort of halfway ahead of the ceiling function. And when we set this as the flow function, it's halfway behind. So the 0.5 plays an important role. Similarly, when we set the k value to be minus 0.5, so it's subtracting 0.5 from the x, it turns into the flow function. So this is basically the formula, minus 0.5, 0.5 and 0. The interesting thing about this is the floor and ceiling values is only to estimate a number to its closest integer. However, with this formula, you can estimate it to nearly, any integer nearby. So like you could, so when h equals 10, for example, the flow function. So, you can estimate it to the closest 10th value at the very bottom, as you know, which the regular flow function, I mean, should be able to do, but it doesn't. So like there's the added playability of that. And same with the ceiling function. In fact, same with the ceiling function over here. So it just moves ahead 0.5. So basically, 0 is for a rounding function, 0.5 is for the ceiling function, and minus 0.5 is for the flow function over here. So basically, it just sort of defines it. So if you want the flow function, flow of x, where x is your input, and h is like where the number you want to estimate it to. For the regular flow function, h is equal to 1. It's going to be, so the k value is going to be k equals minus 0.5. For the ceiling function, x of h, again, for the vanilla ceiling function, h is just going to be 1, k equals 0.5. And for the regular rounding function, where if you wanted to round it to the nearest integer, h is going to be 1 again. It's going to be a k equals 0. Now, this is what I've gotten, sort of a mathematically defined function, or formula you could say, for the flow function, the ceiling function, and my own rounding function. And basically, we're just getting this, the already defined summations to get the job done for us to find. So it's really just a really sneaky way to get the flow function, the rounding function to work for us, and then we just sort of tweak the formula here and there to make it work for us. So yeah, that's it. If you want a written version of the whole thing, I'm gonna be putting my Math Stack Exchange post in the description about this, along with this Desmos graph, so you can play around with it and try to find something new. And if you do find something new, you can put it in the comments, and you know, the link of the Desmos graph as well. And perhaps in the future, I'll be going over whatever submissions you post. Thanks for watching another video, and have a good rest of your day.